All right, just a couple of reminders. Some of you are presenting on Thursday. Everybody's presentation is due on Thursday, whether you're presenting Thursday or Tuesday. So work on that. If that will be a severe problem, talk to me and we can see what can be done about that. You should all sign up for this because you're gonna lose badly.
Are you doing it?
Robert and I are going to.
Oh, you're going to be there?
Oh yeah.
Wait,
so
the
gingerbread competition.
Next Monday. Okay.
Yeah.
I'm signing up.
You need to sign up because you're going to lose badly. And
I think this is closer to composites than it is metal, so I think we're kind of.
Are you building your own?
It could be. Yeah. That could be true. Or
That is not
Are you building your gingerbread?
Is it waterjet gingerbread or?
no, that's soggy gingerbread is no good. No, that's not good at all.
Did Robert used to work for like Universal or something like that?
He worked on roller coasters.
Yeah, he's already got the imagination required.
You work on roller coasters. Yeah, so anyway, and I didn't know he was as competitive as he is, but he's like uber competitive, so yeah, so it's gonna be good. All right.
Project.
No,
No, Jamie's actually.
All right.
Orange season.
Why are there so many different ways that you can weld? Yeah.
Because each welding process would need to change depending on what materials you use, and then also where it's being done at, and the size and scale of what you want to be done, and how thick your pieces are.
Mm-hmm.
For some conductive metals, you could use electrical arc processes, but for metals that aren't conductive, you would have to use different processes.
Are there non-conductive metals?
No, but or if you were doing it underwater or something like underwater welding,
yes,
you would need a different process for that.
Yeah, yeah. So there are times when you either don't have a lot of electricity available, or it would be hazardous to use a lot of electricity. And so, yeah, lots of different ways to do it. There also may be ways that are a lot faster than arc welding. Okay. Any other thoughts? Yeah.
Welding, you have to have some sort of heat, or you have to have some sort of pressure to join the two metals, and there's lots of different ways to either generate heat or generate pressure. So there's a lot of general processes based off of those combinations.
Okay, yeah, just because there are a lot of options of ways of creating a pressure, heat, and a clean surface, and then figuring out how to keep the darned oxygen out of it. So I did way back in the dark ages. So before people knew that 3D printing existed, I did a lot of work on metal 3D printing, and we spent and it was essentially a welding process. So it had a laser that came down and made a little melt pool, and we blew powdered metal into the melt pool, and we could build stuff up from that. And so we made a lot of different parts from that. Always, 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 the whole goal was how do you keep the oxygen out of it. And so for our process, we had a box that was full of purified argon, and we would actually start by welding something over in the corner to suck any oxygen that was in the box, to suck it into that weld, and then we would go weld the thing that we were going to work on. So we'd make a throwaway weld. Did I tell you about that glove box? So it was a positive pressure glove box. So and we needed to keep the argon level around 3 parts per million unless you were doing titanium, and then it had to be lower. But because it's a positive pressure glove box, you put your hands in there and you work with the part inside, but when you pull your hands out, the gloves stick out the front of the machine because it's positive pressure. And so we made these parts. We actually made the first 3D printed metal part in space, and it's on a satellite doing something. I don't know. Nobody could tell us what it was doing because of the function of the satellite. So anyway, it's up there. And it was a 33-hour part build. And so we took in shifts to run it all night long. And the thing was, this machine was a welding process, so it generated a lot of heat. and it was right in front of the thermostat for the room. And so it would generate a lot of heat and throw it on the thermostat. The thermostat would throw on the air conditioning. So the room was just freezing when you would run it for 30 hours like this. It was so cold. So I had a shift until midnight, and I went home and slept for a couple hours, and I came back at 4 o'clock. And when I came back, the operator who was there was huddled up against the machine trying to stay warm because it was on the heat source. But it was so funny because he was huddled up against the machine, and it of course had its arms out, so it looked like it was giving him a hug. Anyway, that's welding in the past. All right, yes, lots of ways to create heat and pressure. What are the critical aspects of any welding process? Heat, pressure,
Clean surface.
clean surface, and a way to control the environment. So those are the 4 things you have to have. The environment, you don't have to have the way to control the environment, but to get a good weld, you need that. All right. So you can do all kinds of welding without heat. So if you try to take a stainless steel screw and screw it into a stainless steel plate, and you don't put any grease or anything on the threads, it will do what's called galling, and it will friction weld itself into place. This is a huge problem in space. Whenever you put a screw into a nut in space, it will friction weld itself there, and because there's no oxygen to oxidize the surfaces to keep this from happening. And so it's a huge, huge problem. Also because in space you're limited on the number of things that you can put on the surface to keep it from doing this. Tremendous problem. All right, that's okay. We'll skip those. Those aren't so important. What is the purpose of slag? Yes?
Slag comes from stick welding, and it's the coating, the powdered coating around the stick that comes off, and it shields the weld as you weld it, and you can knock it off when you're done with it.
Okay, so it keeps it off the cooling metal. So the slag isn't over the melt pool. There is some burning of a material that's part of the slag that comes off. There's some flux in there, and it burns, and it covers the melt pool in a gas, so it's like blowing gas on it. But the purpose of the slag is to cover the melt pool as it cools to keep it from oxidizing. Slag causes lots of problems. If you leave it on there, it will cause deterioration of the weld products. It's a real pain to deal with, but it is a way to get things done. Why is welding done at 50 volts or below? Yeah.
To prevent shocking the operator.
Yeah.
Component of the metal.
That's right. It is the breakdown voltage of skin. So normal dry skin will keep out 50 volts. And if you get above 50 volts, then it can arc through your skin and get to your blood. And that's when bad things happen, because blood happens to be connected to your heart pretty effectively by a bunch of salt water that we call blood. So we keep the welding below 50 volts so that it will not arc to you. Now, you have to be careful, and you have to think about what you're doing, because if your hands are covered in salt water, or if you have a big cut, so that you're holding the torch with that, then the breakdown voltage is less than 50 volts. So you have to be careful and use the appropriate PPE to not get shocked by the process. Electrocution is not very common in welding, but it does happen. So flux, I said, happens. It's contained in the stick when you're doing stick welding, and it shields the melt pool from oxygen. So there's also shield gas in some of the other processes that blows the shield gas on. What might be better or worse about either one?
I thought you just said slag was what keeps the melt pool from oxidizing.
No, slag keeps the cooling metal from oxidizing, but the flux keeps the melt pool. So the slag is on the solidifying metal, the flux is on the melt pool itself. So why do you think one might be worse or better than the other? Yep.
Stick welding's pretty easy to jump in a big muddy pit and weld up a pipe if you just have a stick.
Okay.
Whereas TIG or MIG or any other process, it takes bottles and you need argon or C25 to weld with those, burn those gases.
Okay, yeah, so if you're gonna use shield gas, you have to buy shield gas. And you have to have enough of it, and you have to transport it to the site where you're using it. And so it's not terribly expensive, but it is an expense. It also means that you have to have these bottles around, depending on the size bottle you have. You know, the small bottles are 1,500 PSI, the large bottles are 4,000 to 8,000 PSI. So they are a bit of a safety risk having them around. You have to be very careful, treat them well. So that might be a reason to use stick welding. However, stick welding, the quality is not nearly as good. It's hard to get a good quality. A really good part about stick welding though is that you can just do it with a couple of car batteries if you have the right system. So if you have something where you need to repair it in the field, it's a great way to do that. We don't need to know or weld pipes or those. We just need to be aware that when you're joining things, you have to think about how you're going to put it together. The way that this happens in real life is that you figure out the strength of the material as if it were a material just solid. And then there are ways that you derate the material based on both the weld type and the joint design that you used. And so like if you put a butt joint on something, then it might derate the strength of that piece of material by 50%. And then if you did a groove weld on it, maybe it's only derating by 40%, something like that. So that's how these get applied when you are actually using them and finding them. But you don't need to memorize them. Yeah, basics of stick welding. Yep.
You have like the two things, one would be clamp on the metal part,
Okay.
the two electric like connected clip things, and then the other one you have the stick in it, and you like scratch the surface and it like creates the arc. You like hold it like close to it and it melts the stick into it.
Okay, yeah, so it is an arc process. It is consumable electrode. So as you weld, it is eating away the stick. So the hand that is moving across with the stick is having to get closer and closer to the surface. In that stick, it contains both the filler metal and then it has this other metal that becomes the slag, and it has something that is fluxed also to generate a shield gas around it. Flux core. Yep.
Flux core is like kind of similar to stick, but it's a wire fed, kind of like MIG, but difference between flux core and MIG is flux core has the flux on the inside of the wire, where MIG is a gas around the outside of the wire.
That's right. So flux core has goo in the middle of the wire, and that goo flashes to gas and protects the weld and then blows away very quickly. But it is feeding the wire out, so it is consuming the electrode, but you're keeping the gun the same distance away from the weld all the time. It's kind of the easiest to do and the crappiest welds. So it's easy to make terrible welds with flux core. MIG is sort of the same system. It's a wire feeding it through. You're blowing inert gas around it to create an inert environment and to prevent it from oxidizing quickly while it's still molten. And MIG is really easy to do as well and makes good welds. But you have to have gas for it. And then TIG, the big difference with TIG is that it is not consuming the electrode. You're feeding in the filler metal from a separate stick of material, and the arc is going from the tungsten down into the material. But the tungsten does not go away, mostly. All right, at your table, it's a competition. Write a list of all the things that were welded, that you had some interaction this morning between getting up and getting here. You need to be quiet. Don't say things too loud so the other tables notice.